if you take a look at training hardware, it's kind of gone the way of like building supercomputers, right? People don't talk about building machines anymore. They're like, here's my entire rack, right? This starts looking like, what Cray was doing. So in some ways, you could be like, oh, we're kind of regressed back to the supercomputer era. And I don't know if I use that word positively, right? We're building these like fully vertically integrated systems. I'm not sure that's the route for inference. I think inference is much better served as a large scale workload where you can utilize a bunch of relatively commodity hardware and be able to like scale out efficiently.
All right, everyone. Welcome to another episode of the TWIML AI podcast. I'm your host, Sam Charrington. Today, I'm joined by Zain Asgar. Zain is co-founder and CEO at Gimlet Labs and an adjunct professor of computer science at Stanford University. Before we get going, be sure to hit that subscribe button wherever you're listening to today's show. Zain, welcome to the podcast.
Hi, Sam. Thanks for having me here. Super excited to be here.
Excited to have you on the show and looking forward to digging into our conversation. We'll be talking about the work you're doing around heterogeneous inference for agentic systems. To get us going, I'd love to have you share a little bit about your background.
As I mentioned, I'm co-founder, CEO of Gimlet, and also adjunct faculty of computer science at Stanford. Prior to this, I was a general manager at New Relic through an acquisition of my previous startup, Pixie. And actually, a bunch of people from Pixie are now at Gimlet as well. I was an EIR benchmark capital where the idea for Pixie came out of. I was in Google Research and spent a lot of time at NVIDIA. So I've kind of focused on like efficient compute and being able to orchestrate and run compute efficiently on large scale clusters.
And where did the idea for Gimlet come from? What are you going after there?
So when we started Gimlet a couple of years ago, we had a focus on like how do we actually make AI workloads, at least 10 times more efficient, right? And part of the challenge over here has been that you've seen this like huge explosion in AI workloads, especially around agentic AI, where you're consuming like 10x more tokens. And really, if you want to be able to keep this somewhat sustainable, you need to have these big leaps on improvements. So that was our original focus at Gimlet. And when we started off, we were really thinking about how do we get models to run on things like your laptop and Raspberry Pis or whatever, right? Like small scale hardware. And how do we get like the
Kind of
best in
edge
class
devices?
efficiency? Exactly, any kind of edge device. But one of the things we kind of realized is that, we built up our stack to work on this very, very heterogeneous system, right? Because like, two MacBooks look very different than, typical Windows laptops running like Intel or AMD CPUs, which look very different than like an iPhone. And we got really good at running models efficiently. So we kind of realized that this technology that we've built up is actually pretty applicable to data center scale systems. And, there's this large scale problem. And so we could have a much larger impact if we actually improve that system. And, our team decided to start going after that space instead of like directly targeting edge devices. Partly because, we think that the edge market still needs a couple of years to really materialize.
Whereas the data center market is crazy hot right now.
Exactly. And I think, the fact that we can basically orchestrate and run stuff across many different hardware to optimize like the unit economics and also get best in class performance is like a big benefit over there.
One of the things that you guys talk about is specializing in compute for agentic AI workloads. Does that just mean LLMs and multimodal models, or is there something specific about agentic that you think needs to be considered in the hardware?
So one of the things, we started to build for is like, how do you run like entire applications, right? Like today people run agentic frameworks. Those frameworks typically call out to different APIs to run models, which lends up meaning you spend a bunch of time doing all these API calls and orchestrating API calls. We kind of wanted to take the approach of like, well, what if you could avoid all the round trips and put everything in a single system? And agentic systems as a whole are very heterogeneous, right? Because there's a bunch of like, CPU compute happening. There is a bunch of, things like database calls, et cetera, et cetera. And there's a lot of like LLM model execution. And if we can better orchestrate all of those and understand when and where things are going to be run, we can both improve the efficiency and the latency of the system, but also be able to make optimizations within the models themselves because we know how they're going to get used.
Got it. And what kind of optimizations are you typically looking to make?
Yeah. So one of the things we do, one of the biggest things we do from an orchestration perspective is just like right sizing the hardware. right? Today, general consensus is that people will go buy like the highest end hardware they can, which, is basically a B200. And you'll basically maximize how many ever B200s you have to run your model workloads. One of the things we do is actually do pretty fine grained partitioning of all your models and including your entire we think about an agent as an entire like data flow graph. So how do you actually like break up the data flow graph? How do you break up the models so you can assign the most performance critical pieces to the highest end hardware and then offload the less performance critical pieces to hardware that will be better utilized by running that workload?
What you're describing reminds me of a conversation that I had with Lin Chow at Fireworks about kind of the way that they're approaching distributing inference across their cloud environment. I imagine that anyone who's dealing with inference at large scale is going to be thinking about how to do that kind of distribution. Does the heterogeneity add a particularly interesting element to it?
So once you have like any kind of large scale, so people typically talk about, things like prefill, decode, disaggregation, where you run prefill on one set of nodes, decode on another set of nodes. When you started looking at heterogeneity, especially if you look on heterogeneity across vendors, right? This problem exists both within a vendor and even across vendors. You start having to think about a lot more of the trade-offs of like, what is my cost of compute? What is my cost of memory bandwidth? What is my cost of memory capacity? And then, it's basically this giant optimization problem of like figuring out where to put which workload in order to optimize the cost per token.
And is that something that you are thinking about on a real time basis, like a runtime basis, or is this more of a deploy time consideration where it is, when you're deploying an agent, it gets kind of introspected and you determine what should go where at that deploy time?
It's a little bit of both because when you first deploy it, you'll probably have a good estimate of where things are, but it's pretty, most of these workloads are complicated enough that it's pretty hard to know exactly where things are going to land. So there is a whole bunch of like, profiling that goes on after the fact. So like observability and stuff kicks in, and then you get a better idea of like how to change the allocations in order to improve the performance. So in our system, we actually have two paths. Like there's the fast path where we just try to get something up and running. And then there is another path which tries to move the workloads around to like optimize the utilization of the hardware. And then on an API perspective, there's a whole bunch of like routing decisions that need to get made because you need to know where the data is available, what's cached, what's not cached, and where the models are loaded. You might be offloading models into CPU memory and things like that. So you need to know like the cost dynamics there on a real time basis.
I'm imagining a kind of an optimization problem or a control loop where you've got like a Kubernetes cluster with a bunch of different stuff in it. You coming from New Relic, you mentioned observability, you've got a bunch of monitoring types of tools, and you're kind of mapping all that to some kind of costs factors and using that to moving things around in that kind of environment. Is that kind of close to the way you have mapped things out?
Yeah, that's actually not far from how our thing works, right? We run completely on top of Kubernetes. And, we actually use some pretty cool new stuff like DRA and Kubernetes to like really help like orchestrate some of these workloads.
Oh, what's DRA?
It's the resource allocator, dynamic resource allocator. So it basically allows you to like, be like, oh, I have this many slices of capacity available. Like, how do I actually route
Oh,
to?
nice.
Yeah. So we can actually like, instead of like thinking of a GPU as like a full resource, we could be like, oh, here's like a quarter GPU worth of work.
Oh, interesting. I'm trying to remember the name of the company that used
Run
to
AI.
do Run AI. Yeah, they were acquired
Yeah.
by Intel, I think.
NVIDIA.
NVIDIA. Yeah.
Yeah.
And so now that technology is more readily available.
Correct, but, it's really not supported on GPU hardware per se, so one of the things we do is actually really make it easy to run workloads on, like, GPUs and other accelerators while, like, partitioning it into these segments. But we rely on Kubernetes to help orchestrate it because we don't wanna rebuild everything, right? So we wanna rebuild the pieces that matter and then rely on the high level frameworks to provide us the hooks necessary.
So does Kubernetes DRA already support GPU partitioning, or is it a broad framework and you have to plug in the GPU bits?
It's a pretty broad framework, it's more just for doing, like, dynamic resource allocation, so we basically put in the GPU bits over there. And DRA itself is actually not in GA in Kubernetes yet.
Okay.
It's supposed to get
Interesting.
released in the next version, I believe.
Okay.
So the challenge that really comes in, I think, when you deal with heterogeneous stuff is, there's kind of like two things. Orchestrating on heterogeneous hardware is more challenging because the networking fabrics and stuff could be pretty different. So you have to figure out like how, these, because people are typically running very high speed network fabrics, so like 200 gigabit, 400 gigabit, 800 gigabit Ethernet. Sometimes they're running like, infinite band or something more proprietary, like even NVLink across like a rack. And you have to kind of figure out how you can actually orchestrate across these different fabrics. And every single hardware has, a different programming model, right? They're not, most of them, obviously NVIDIA uses CUDA, but there's a whole bunch of other factors if you're targeting like Intel and AMD hardware.
Yeah, talk a little bit more about why that networking heterogeneity causes challenges. I think, folks that have been in the space long enough think back to the OSI 7 layer stack, and at some point we should be abstracted from all that that underlying detail. But that is not the case here.
I think we're getting there slowly, right? Like for example, at Gimlet, most of our stuff runs on top of this thing called Rocky, which is RDMA over converged Ethernet, right?
Okay,
RDMA was like doing
that's
like remote
remote
DMA.
direct, remote
Yeah,
DMA. Yeah.
yeah, remote direct memory access. So it basically tries to emulate like memory semantics over a network interface. And you really need stuff like this because you're like, oh, I want to move data between two different accelerators, right? And the fastest way to do it is to be like, oh, here's this chunk of memory. I'm just going to send it over to this other machine. Um, the challenge you typically run into with this type of stuff is, you know, um, you don't usually want to traverse the CPU while doing it. um, right? Because you don't want to have the CPU do like a call to the GPU, capture the stuff into CPU memory, and then copy it out. So there are things like GPU Direct that actually allow you to do this, and they're pretty mature in the NVIDIA ecosystem. And they're usually relatively mature if you go within like a single vendor, right? Like if you want to say I want to copy from AMD to AMD, it's like relatively straightforward. Um, the problem you run into is like when you want to copy from one machine to another, they may not be able to transparently do it. So there's a whole bunch of like, systems engineering that happens over there. Even if you're trying to transfer like caches and stuff, they may not even be in the same formats. Which means I could maybe apply some like transposes to move data around in order to actually get it to properly map to other hardware. And all of this is in a spot where, milliseconds matter or maybe even microseconds matter.
Gimlet operates a Gimlet cloud, but it also sounds like a big part of the heterogeneity that you encounter has to do with disparate customer environments. What's the split that you tend to see between usage on your cloud versus usage in customer environments? Is there a focus? Is one more of a focus than another? Like, how do you think about that?
Gimlet, as of today, we haven't publicly launched our cloud product. We have like a handful of like early access customers on our actual cloud product. Almost all of our sales, and we do about 8 figures of revenue right now, have been through data center customers and partners on the semiconductor side. And over there, it's mostly self hosted.
8 figures is not bad for a company that launched 2 weeks ago.
Yeah, well, we've been working on it for a little while under the radar.
Talk a little bit about the licensing model. Like, is that primarily software licensing? Is that also hardware provision? Is that, how does that all work?
So today we've been mostly going to like semiconductors and data center side partners, and that's been a software license. And it's usually restricted to some number of nodes, or there's an additional percentage licensing fee based on how much hardware you utilize. Um, and then on the cloud side, when we're planning to launch our product in Q1, that'll be much more of like a usage based pricing.
So we've talked a little bit about some of the technical challenges, networking and heterogeneity. Like, how does that lead? Those all sound like areas for compromise, but you're also targeting. You mentioned 10x performance as kind of an initial vision. You mentioned better performance and better cost per token. Like, how do you overcome those challenges, those compromises, and get to something that's actually better?
So we think about, at the highest levels, we think about our stack kind of as this like 3 layer cake, right? So you give us like the agent graph, which is basically a data flow. And as of today, we can basically absorb, things like, LangChain, or even people have written like Python code around like Hugging Face or whatever, right? Like we can absorb that stuff into our system directly. We don't have like our own like agentic interface or something. we expect people to come in with their own workflows. So we want to meet developers where they're at.
And do developers need to like call some libraries if they're like in a pure Python non-langchain type of environment or
Yeah, when you import Gimlet, we do a lot of our stuff relies on like doing tracing through the Python code. So it is currently only usable through Python. That might change in the future. But as of today, it's basically stuff written around Python or around like other libraries where we can generate a graph out of it.
so it might be analogous to how you might use a Langsmith or something like that, where you're decorating functions that call out to LLMs, that kind of thing.
Right. Except on our side, we expect people to just use whatever system they're using, and we intercept the calls and figure out how to map it into our system.
Okay.
So we don't have like our own like decorators.
Oh, okay. Got it. Got it. And so you're intercepting the calls at the Python function level. And is the implication that you're, then potentially, the natural kind of place for that to run is like on a local, GPU, et cetera, but you're kind of, remoting that out to wherever it needs to be running?
Correct. So when you upload it into our system, we'll basically run through it and be like, okay, here's the graph that we know, and then we'll separate out the models to be able to go run on GPU resources. And we know like, for example, if you import a model from like Hugging Face or something, we'll know exactly what model it is and bring it into our system. And it's all pretty automated. Like our goal is 5 minutes from like, hey, I have this like thing that runs locally to I want this scalable in the cloud.
Yeah. And are you limited to specific models, to published models, or if you've developed some custom model, can that be used as well?
Yeah, so our whole system's designed to be able to run on any type of model. We actually support like more than LLMs in our stack as well. We have like support for several different types of models, and so that kind of goes into like how we architected the system. So once we have like our the agent graph, right? The first layer that we do is we think about as like workload disaggregation, which is how do we actually figure out what are the granular components of this workload and how to split it up in some meaningful way. And this is actually where the vast majority of benefits come in because knowing what hardware is available and how to split it up, you can go ahead and start like packing these things in pretty tightly into the different resources. And this is also where the cost modeling comes in. You start thinking about, what is my cost to compute on all these different hardware? What's my cost of memory bandwidth? What is my cost of memory capacity? And you start figuring out what are the critical resources for each one of these sub pieces of the workload. And then you can then allocate it to the lowest cost resource. Right, and of course, all of this is within some SLA bound. So, like very technical terms, like this lines up as some like big convex optimization problem, right? With a bunch of different assumptions, and you try to just like optimize this down and figure out here's the optimal allocation. In real life, it's very unlikely you'll be able to get the optimal allocation because the hardware resources you want may not be available. So you'll just try to, find the best fit. Um, very deviate from the optimal. The next layer down is that we have our compilation system, which will basically take all these workloads and lower it to the target hardware. And when you do that, this is where we do all the optimization around like, okay, well, this stuff runs on like a CPU, this stuff runs on a GPU, and we'll, go and compile that stuff down. The challenge you typically run into with any kind of, generic compiler framework is that you usually land up with like at least in the AI space, you'll end up with like relatively unoptimized like kernels. So we have a framework underneath it where we actually autonomously rewrite your kernels using LLMs in the background to try to generate like more optimized code to run on like every, like to run most efficiently on AMD hardware or Intel hardware or NVIDIA hardware.
You said you're using LLMs to do the compilation?
So for the first layer in the model compiler, we used MLIR plus Torch MLIR and LLVM to do the compilation. And then the layer below that, we have like automatic kernel synthesis, which is basically like take all the compute code that's running and how do we generate better compute code. Um, and that's actually done using LLMs.
And did you have to post train a model to do that or fine tune?
It's all post training.
So can you talk a little bit about that process?
Yeah, yeah. So actually, for reference for the readers, for the watchers, sorry, there are actually a few blog posts on our blog that talk about this in lots and lots of detail. But at a high level, it's like a multi-agent system, right? So it's like a Gimlet hosted multi-agent system in our own stack. Uh, But basically, what it does is there's a part there's like a supervisor based model which tries to generate new kernels, right? So you give it your PyTorch input. In our case, it's usually PyTorch because that's the only code we really optimize. So you give us the PyTorch input, and then we can give it reference code if we have it available. So, for example, we may have CUDA reference code available, right? Because there may be a CUDA version of that kernel available. If not, it doesn't matter. It's not required. It's a hardware in the loop system, which means that the first agent will actually go and generate a whole bunch of candidate kernels. We will then go run this candidate kernel on the target hardware, and we'll do all the profiling and correctness checking. Because typically, when you generate new kernels, there's always challenges with correctness. So you need to go run all the tests, make sure it's correct. We capture the profiling data, and then there's another part that basically looks at the profiling data and says, okay, try these new techniques to optimize the kernels further, right? And then the first generation part again will go regenerate new kernels based on the optimization criteria that it thinks it needs to do. And then you kind of repeat this loop a few times until it converges. And if you get a faster kernel, you use it. If not, you just fall back to the previous implementation.
Interesting. And is the correctness testing that you're doing, is it, does it run or is it, somehow faithful to the original PyTorch code? I guess I'm imagining that you could produce valid kernels that run, but, somehow have, slight deviations from the original algorithm.
Yeah. So what we do over there is that we actually run through a bunch of numerical tests to make sure that the kernels are numerically equivalent. The caveat over
Meaning
here
you're
is that,
doing some kind of sampling of
yeah,
the input space and using that to
exactly.
determine. Okay.
The challenge over here is that it's basically impossible. Well, maybe that's a strong word, but it's very hard to generate a completely numerical equivalent kernel because of the way floating point math works, right? And this is actually part of the challenge because you look at this problem, you're like, oh, we can just prove that they're equivalent, right? But it's actually not that easy because, you know, if A times B is not the same thing as B times A, things start looking really weird, right? And that's where you are with floating point math. And because of that small like precision issues, it actually makes this problem pretty difficult. So we're actually working on some research um, to um, to show like what is the impact, like how do we understand what the impact is of accumulating these inaccuracies in the loop.
Does that imply that some type of quantization or quantized models or something like that would be more easily optimized because you don't have the floating point issues, or are they two different areas of floating point?
Well, I think a lot of people quantize into like a lower precision floating point now, like FP4 or whatever. So like ultimately you still have those issues, but the good thing about FP4 is there are not that many possible values. So it's actually a little bit easier to verify. Obviously the higher the precision, the harder it is for us to verify correctness and knowing the exact bounds. So when we do the kernel generation, what we do typically is that we cache all the kernel gens offline for like a whole list of models and then verify them and make sure to put them back in. So we try not to do it in real time because we're still afraid of like potential numerical errors in the system.
Yeah, it strikes me that, like, if you were talking to me as a customer and explain this, and like, I'm not sure that I want an LLM in my, compilation and optimization step, just given hallucinations and all that kind of stuff. And, given that that they're difficult to verify, like that seems like that would discourage me. Do you find that? Like,
Well, so normally we tell people that we can generate them optimized kernels, and people are pretty excited because they hear about this new technology, right? But like I said, we tell people, hey, don't worry about it because we have basically run it offline and made sure that these kernels are correct, because we're not ready to run it like the third layer of a cake doesn't run in the loop right now.
and so the argument then is that the sampling based verification, you feel like there's sufficient coverage and you can flesh out any issues.
Yeah, and at the end of the day, we basically, once we are running a set of models. Like we always verify, some set of models, right, and make sure they're correct, and you can just get the performance scores on the model and see that they still match.
And so we got as far as the second layer of the cake. Did we get the third layer of the cake yet?
The model compiler itself is fully, LL compiler based, right? So it'll never generate code that's not accurate. We did get to the third layer, which is the kernel optimization that happens automatically. And to be honest, the way I would think about this is that, what would happen before is that we would have our compiler would, spit out a bunch of code, and then our team would go by and be like, oh, we think we can write this to be even faster, right? The problem is that, it's easy to do this when you target like one hardware, like one piece of hardware. It becomes like untenable. Our team's not very large, right? It becomes untenable when you start thinking about targeting, hardware from like three different vendors and multiple generations of hardware in each vendor. So then you start, thinking more creatively, and then we're like, oh look, these are the steps that I take to optimize the kernel, right? Like I write a more optimized kernel, run some benchmarks on it, figure out why it's not as performant as I think it should be, make some changes, keep doing this until I get a good kernel. So we're like, hey, why not build an agent that does this? And if you like the results, we keep it. If we don't like the results, then we will go write it manually. So ultimately, while we talk about these three layers of the cake, the third layer of the cake is really how do we cut down the amount of work we need to do in order to get a functioning system at large scale. And over time, I think you'll start thinking about like how do you apply AI to systems as a whole, right? But I think we're not. I think you're right in the sense that if you go start telling people all these decisions are getting made by LLMs, they're probably gonna get a little upset. So we don't really run the LLMs in the live loop today, but we do see that changing over time as better guardrails and better testing infrastructure comes online.
What are some examples of ways that you would see them as being useful?
So I think there's an argument to be made, for example, that even in our planning system where we figure out how we're going to orchestrate these workloads, we could have like an LLM help in the planning, right? Like right now we have all these rules and all
It's
these
kind of rules
benchmarks,
and
but you can start,
heuristics. Yeah.
yeah, exactly. You can start thinking about there being some kind of like, like a tool, like an MCP tool or something that says, oh, I will tell you exactly what the performance of this hardware is going to be for this workload. And you can build this out in like a much more structured, like, LLM goes and examines all these things and then, figures out how to plan this stuff out. We aren't that sophisticated yet, right? Most of the planning is done using just like, heuristics and optimization criteria. But it'd be pretty cool to see like, systems that can actually use all the live information to do this over time.
Yeah, I'm thinking about the like TCO advantages that that you're targeting, like better cost per token. Like, have you do you have a sense for like how much of that comes from each of these layers of the cake? Like how much of it, if we just disaggregated the workloads and kind of put them to the most efficient or the best cost hardware for that workload, like that would be 60% of the benefit. And then compilation is 30 and kernel is 10, or is it like, the other way around, like, 20, 40, 40, something like that?
Yeah. So I think it really, really depends on what hardware you're targeting, right? Because if you're targeting something like say like, at the end of the day, you're thinking about just think about the model workload that's easier to think about, and that's the vast majority of the compute. If you think about something like that and you're trying to run on top of H100s, right? The code is like very, very well optimized at this point, which means that at the kernel level, you're just not going to get all that much, right? Because it's been optimized for years at this point. Um, and like ultimately, we can talk about how machines might be able to do a better job, but hundreds of people hammering on something for years will probably get you pretty close to the best answer there. Um, and I think if you take a look at stuff like H100, we see like single digit percentage improvements, right, at the kernel level,
At the lower levels, yeah.
at the lower level, because it's been so hammered out, and it's something that you can figure out like statically, like oh, I have to run this deep seek model. Here are all the optimizations I need to do in order to make this performant on an H100. Interestingly, if you start looking at even like an RTX 6000, right, which I think is like a B40 or a B200, you'll start seeing like much more significant gains to be had over there. We have seen 20, 30, 40% improvements in performance in many cases. And that's because it's it's a lot less explored than the Hopper optimizations have been. If we start taking a look at, things like kernels on, Mac hardware, kernels on AMD and Intel, we also see like significantly more improvements, like, and sometimes even like over 2x. Uh, and that's partly because like some of these frameworks, like Apple, for example, they don't have a properly working like Torch compile equivalent. So we get a lot of benefits because you're comparing against like relatively unoptimized code.
So we've been talking about Intel, AMD, and NVIDIA, but you also support deployment on the M processors.
Yeah, we've always, like I said, we started off as an edge company and we have a
Uh-huh.
soft spot for edge hardware. So we always have dreams that we'll eventually have a fully distributed cloud where we can run stuff in the cloud and run stuff on end hardware and have it orchestrated between both of them over time. So we play around with those dreams all the time.
Nice. And do you have anyone running on Mac hardware kind of in the data center? Like, is that something that people are doing?
I'm sure people are doing it because I think like probably Apple and other folks like that will be incentivized to do it, but we don't work on that doing that today on data center side.
When you say you don't work on it, mean you don't have anyone doing it, or the product doesn't support it yet?
Our product could run on Mac hardware because we do support that, but we haven't done it at data center scale ourselves. Only on end user side things.
Okay. Okay.
But yeah, your so the kernel area, somewhere between single digit percentages to maybe like, a 2x improvement exists over there based on what hardware you're looking at. Could be even more if you're running on very unoptimized or new hardware, right? Um the the compiler side, it's mostly around just like doing better fusion, figuring out what all the stuff is. Probably at this point, if you compare against like best in class, maybe you're looking at single digit percentages, maybe 20, 30% over there. And some of that is just because we're trying to build, the main challenge of the compiler is not the optimizations, it's just being able to apply these optimizations across different vendors' hardware. And the last layer of the stack, I think, is where the vast majority of benefits exist, right? Like a lot of times you hear people say things like, "Oh, my GPUs are only like 30% utilized," right? And what that ultimately means is that you're wasting like 2/3 of your GPU capacity. So there's a fair amount of like optimization work around just more efficiently utilizing the hardware you have available. And that's where I think the vast majority of the benefits are.
Do you come across interest in applying heterogeneity for like training scale, or is it primarily interested? Like, is there like what are, if so, like what are the structural, if so or if not, like are there structural reasons why folks are or are not trying to do that?
I think on the training side, when people talk about heterogeneity, it's usually still heterogeneity in a homogeneous sense where they're like, okay, I have an NVIDIA cluster or I have an AMD cluster, and they don't ever try to mix the resources. And part of the reason is like, if you take a look at training hardware, it's kind of gone the way of like building supercomputers, right? Like, people don't talk about building machines anymore. They're like, here's my entire rack, right? This starts looking like, what Cray was doing like 40 years ago or something, where they're like, oh,
Yeah.
here's like an entire rack of machines. So in some ways, you could be like, oh, we're kind of regressed back to the supercomputer era. And I don't know if I use that word positively, right? We're building this like fully vertically integrated systems. And I'm not sure that's the route for inference. I think inference is much better served as a large scale workload where you can utilize a bunch of relatively commodity hardware and be able to like scale out efficiently. And I think the only way this becomes like scalable and sustainable is if like you can interoperate easily with different hardware. So I do think that there's going to be some divergence over time. And I think you're going to start seeing this. Like even Nvidia, for example, announced their CPX, which is their context processor. It's a way that heterogeneity is making its way into the workload, even within a single vendor, single generation.
Yeah, but there are certainly vendors that are pushing the kind of supercomputer profile, rack scale solutions for inference. Thinking of folks like Cerebras, thinking of folks like Qualcomm, Samanova. The same ideas apply, but it sounds like you're seeing a lot more heterogeneity on the inference side.
Yeah, I just think that, as systems tend to scale out and mature, they tend to become more disaggregated over time and not more aggregated.
And maybe over time, all of the new expensive hardware goes first to training, and then inference gets the hand me downs.
Right. And I think in most cases that'll be fine, right? Like, you might need some of the highest end hardware for the most performance critical work, even on the inference side, but then you can use a lot of the older hardware to then do the inference.
Can you talk a little bit about like just to make the conversation more concrete, like specific workloads or use cases or customer experiences?
Yeah, so we've deployed on a bunch of different heterogeneous hardware at this point. I think there are some numbers that you've probably publicly seen from us on our blogs, and maybe even from some semiconductor companies. For example, we showed that if you utilize Intel's Gaudi processors, which are relatively old at this point, um, and mix that with like a B200 or mix it with an H100 or H200, you can actually get pretty significant TCO benefits. Um, and the reason for that is, you're basically, if you think about the different workloads, you're essentially looking at what is the cost of compute and the cost of memory bandwidth, and the Gaudi has like extremely low cost of memory bandwidth because it's an HBM chip that's relatively low priced. So if you can start to think about how to utilize that difference, you can actually get pretty significant cost benefits on that. And because it's so much, relatively so much cheaper, you can use a lot more of them and essentially make up for all the perf differences you have. And we can pack the most performance critical workloads on like a B200. So from a user perspective, they can't really tell, but the cost is actually substantially lower.
Have you talked to the folks at Qualcomm? They have their AI inference systems. Like they just announced the AI 250 and AI 200 systems. Seems like one of the things that they are talking about is inserting themselves into these heterogeneous environments. And I would imagine that something like what you're offering might facilitate that.
Yeah, I think it would be useful to them. We're just in like very early conversations with them, to be honest. Um, but I think it makes a lot of sense. Like one of the things that everyone thinks about is that most of these data centers and most of the customers like have a very high preference to buy large scale NVIDIA hardware, right? Because that's the default. Everything's going to work on it. So the reason heterogeneity is interesting from a business perspective to other semi companies is that it's an easy way for them to go to their customers and be like, hey, if you buy a few of these on the side, we can show you the benefit of heterogeneity. And then you don't have to like wholesale make large bets on
You don't have to rip and replace. Yeah.
exactly.
Yeah.
And in particular, it makes the story easier if you're competing against, potentially depreciated, older NVIDIA capacity, right? It makes it easy for you to say, oh, I can utilize, you know, all my old NVIDIA capacity plus some of the newer capacity from a different vendor and then see what the changes are over there.
Your typical customer deployment is like clearly heterogeneous in terms of infrastructure. Are they, similarly more heterogeneous in terms of use cases and applications, or are they, more homogenous? Like they are, running this to support a single application or a single, agent or set of agents at a large scale.
It's mostly the latter. The applications we typically see that are running in a lot of the data center stuff that we target, they're relatively homogenous because they're usually utilized by like one or two or three customers. Um, Most of the deployments that we're seeing have like basically heavy hitter customers, and then to serve like a large scale, they're going to have a whole bunch of really small workloads. But for the most part, the vast majority of the workloads are coming from like a couple of different players.
Okay, so it's not necessarily something that, for example, like uh, a CSP cloud service provider might create a general purpose inference cluster using your stuff. It's more, I have this workload and I need a place to run it and try to drive down cost per token.
I mean, they could a CSP could use our stuff, but these days we've mostly been targeting people who have either their own data centers or like think about like sovereign clouds and other neo clouds.
Have you seen a lot of, talk a little bit about what you've seen in the sovereign cloud space? Like I hear that uh, thrown around a lot, not a lot of use case examples, in part because of the sovereign nature of it, perhaps. What are you seeing there?
Yeah, so I think even amongst the sovereign clouds and neo clouds, there's a few different classes over there. So there's some people who have like pretty good, usage of their clouds. And there's some people that are building cloud capacity, but it's not entirely clear what applications are running on there just yet. And a lot of it, I think, is a software gap. Um, we try to target people who are actually using their stuff because it gives us better feedback on how to improve our things. Um, there's also a class of like, say, the sovereign clouds who are building data centers up, in even in the US. They're not like US sovereign clouds, but they're external sovereign cloud companies that are building capacity up in the US. I think they have like a lot of real workloads because they're basically selling that capacity to other customers. So those are interesting people for us to work with because they have like actual usages. And then one of the other things that kind of drives sovereign clouds is because of all the export restrictions and everything, they're pretty limited by what hardware they can get, which typically makes their data centers like heterogeneous by almost by design because they're just getting like whatever they can find. So that actually is a pretty interesting area for us just because we can enable the usage of all that hardware.
Along the lines of like talking about Mac and talk or the M series chips, talking about Qualcomm, are you do you anticipate that your focus will primarily remain NVIDIA, Intel, AMD, or are you anticipating like an extreme level of heterogeneity where you're supporting, there's kind of a long tail to it?
Yeah. So what I want to say is we have support for all these different vendors, but the vast majority of deployments that, we go into or look into are still, mostly NVIDIA shops. Um, and even within NVIDIA, the heterogeneity is like pretty interesting, right? Across different accelerators, there's different cost economics and stuff. So we can still utilize that and orchestrate things. Um, there are a few people we're talking to that want to have data centers with extreme heterogeneity, and these are mostly on the sovereign cloud side. And that's because of the issue that I said, they have so much capacity they can get from each vendor. So they're like, okay, we're going to put all of them in here to get the maximum capacity. Um, but for the most part, what we find out is that people have like two vendors in their data center. And that's partly because, we're solving one layer of the stack. But, as you start thinking about all this heterogeneity, just doing the system management and everything across a lot of different vendors is a lot of work. So people tend not to have more than like, two, maybe three at the most vendors in their actual data centers.
And is the heterogeneity that you're seeing at like the rack scale or the, rack of racks type of scale, or is it, even more distributed than this? Like many years ago, um, startup that I worked at was really kind of on the cutting edge of like distributed systems, and like we would go in and like stand up these environments with like literally like a cast off of this, like some Dell DL240s, like a little bit of that, like very very like part of the idea was that you could, create enterprise grade, SLAs on commodity compute. And, that idea has surfaced in a lot of different ways in the industry over time. Are you seeing like that level of, or are you anticipating that level of heterogeneity? Or is it more like I'll have my, rack of H100s next to my rack of slightly, newer, older gear?
Yeah, normally it's a little bit farther away than on a single rack because usually single rack people will have the same type of machine on. It's especially with like the vertical integration that happens on all these machines. I guess maybe if we take a step back, there's pretty much like laws of physics limits on how many machines and capacity you can have per rack, right? If you go to like a generic data center, you can maybe have like 20 kilowatts a rack and you can't really stack like a ton of machines. So you'll actually see a lot of data centers that run GPUs that aren't optimized for GPU workloads typically have like, just a couple of machines in each rack because you're going to exceed the power budget of that rack. If you go past like, 25, 30 kilowatts, you need to start having, back of rack cooling or like a rear door heat exchanger is what they call it. Um, and that usually requires some level of outfitting, right? So it's liquid cooling, but liquid cooling going to a radiator in the back of the rack. And then if you really start, going to, 100 kilowatt plus racks, you start going into like direct to chip cooling, right? Which is what like a lot of the greatest data centers would use. And once you get to that point, you're basically building like a very rack level system. So typically, if you're like not super sophisticated, you have like one or two machines a rack because that's all you can do. And if you're very sophisticated, you have all these things packed in super tightly, but then now it's very vertically integrated. So either way, you're not seeing a lot of heterogeneity on a single rack because there's just not that much space one way or the other.
Yeah, so essentially the GPU and the cooling and power requirements kind of take you out of that uh, kind of super heterogeneous, like stack up a bunch of commodity stuff. Like it tends to be more. Got it. Okay.
And that might change, right, as like lower power systems and more optimized systems come off. But the industry trend so far has been to try to increase
And maybe smaller models as well.
and maybe smaller models, yeah. But the industry trend, at least on the hardware side, if you look at NVIDIA's roadmap, is that they're actually putting more and more things on the rack, right? Like I think their next generation rack, which is Kyber, is going to be like 600 kilowatts, right? It's like almost an entire data center in like a single rack.
Yeah. Any thoughts on like from where you are today? You've been at this for a couple of years. Recently launched though, a lot of early success. Like how you see things evolving over the next year.
Yeah, so we are super excited about. Sorry, we're super excited about getting our agent cloud launch, which will be more of a developer facing product. Like so far, we've been going mostly to like data centers and et cetera. But I think our heart is really into like going into a developer facing product, working with developers to make running like these models and stuff like much cheaper and easier and faster.
Actually, as you started saying that, I was going to say like if I'm a developer and you're not, offering me a framework, do I care much beyond like the cost per token and the feeds and speeds of the performance ultimately? Like, what are the qualitative reasons why I'm going to care about running on your cloud as opposed to someone else's?
Yeah, so I think the areas that will have a lot of capabilities around are one is like orchestrating all like the large scale agentic workloads, including like asynchronous work and stuff. Um, that's been a big area where people have asked us for like, oh, I want to make a whole bunch of batch model calls and stuff by a bunch of like asynchronously running agents. Like we can support that pretty easily in Gimlet. So that's actually a big part of it. The other thing is obviously the cost economics and performance, and just like the observability around how these workloads are running.
Well, Zane, thanks so much for jumping on. And I feel like this was a bit of a rapid fire chat about what you're up to, but I learned a lot and it's interesting stuff and looking forward to keeping tabs on it.
Thank you. Thanks again for taking the time.
Yeah, thanks so much.